high desert of Southern California, winter of 1883. While fellow homesteaders installed cast iron stoves shipped by rail from back east, former carpenter Thomas Carter mixed clay and straw, building something different around a framework of sticks. His neighbors called it wasteful. They called him backward. Why build from mud and sticks when proven iron technology had heated frontier cabins for decades? Then the killing cold arrived. 48 consecutive hours below zero, winds at 30 miles per hour. The brutal test challenging every heating system in the territory. Standard cast iron stoves failed. Neighbors' cabins plummeted to 25 degrees. Pipes froze. Livestock died. But Carter's primitive contraption maintained 55 degrees while burning half the wood of his neighbors' modern stoves. What did this quiet carpenter understand about heat that decades of iron stove engineering had missed? The year 1878 marked Thomas Carter's second winter in the high desert country of Southern California, where the former carpenter from Pennsylvania had claimed 160 acres adjacent to the old Ramirez Rancho. The landscape stretched endlessly, sagebrush and Joshua trees punctuating red clay arroyos that baked under summer sun, but surrendered their heat completely once darkness fell. Carter had learned this the hard way during his first winter, when interior temperatures in his timber-framed cabin plummeted despite the $30 Acme cast iron wood stove he'd freight-hauled from Los Angeles at considerable expense. The stove represented modern frontier wisdom. Cast iron promised durability and efficient heat distribution, a significant advancement over crude stone fireplaces that frontier families had used for generations. Stove dealers promoted the latest models with scientific enthusiasm, citing improved airflow design and radiant heating principles. The Acme Model 4, with its nickel-plated trim and patent-pending firebox configuration, seemed the logical choice for a man building a permanent homestead rather than a temporary shelter. Carter's neighbors had made similar investments. Samuel Jenkins, whose claim bordered Carter's to the north, had installed a larger Detroit Stoveworks model that cost $42 including freight. The Kowalski family, Polish immigrants who'd arrived the previous spring, trusted their $28 Pittsburgh Iron Works stove to heat their soddy through the winter months. These were educated decisions based on available technology and collective frontier experience stretching back decades. Yet Carter's first winter had revealed critical flaws in the system. On a January night when outdoor temperatures dropped to 12 degrees above zero, his cabin's interior fell from 68 degrees at bedtime to 32 degrees by dawn, despite burning through nearly half a cord of precious oak. The thin iron walls absorbed heat rapidly during active burning, but released it just as quickly once the fire died to embers. Carter found himself rising every 3 hours to feed more wood into the firebox, burning an additional cord beyond his calculated winter supply. The problem extended beyond fuel consumption. Cold drafts infiltrated through floor cracks as the stove created negative pressure, drawing frigid air into the living space. Water buckets froze solid 18 inches from the stove. Moisture from cooking and breathing condensed on interior walls, creating ice formations that didn't melt until mid-morning. Carter's livestock suffered similarly. His milk cow's water trough froze despite the small tin stove he'd installed in the lean-to barn. Jenkins experienced identical struggles, but attributed them to insufficient fuel rather than flawed methodology. He simply purchased additional cordwood from Mexican woodcutters, burning 3 full cords that first winter while complaining about the expense. The Kowalskis rationed their heating, allowing interior temperatures to drop into the 40s overnight rather than bankrupt themselves buying fuel. Carter's education began through observation rather than books. Jose Ramirez, whose family had worked the adjacent ranch since Mexican territorial days, maintained a small adobe horno behind his quarters, a beehive-shaped outdoor oven built from local clay mixed with chopped grass. Carter noticed how the oven retained warmth for 12 to 14 hours after Ramirez's wife finished baking bread, radiating heat well into the following morning despite containing no active fire. The principle intrigued him. While his expensive iron stove cooled within hours of the fire dying, this simple clay structure held and released heat gradually over half a day. Carter examined the construction. Thick earthen walls, approximately 4 inches deep, built around a temporary wooden framework that burned away during initial firing, leaving a hollow chamber surrounded by dense thermal mass. Ramirez explained the technique through broken English mixed with Spanish, describing how his grandfather had learned the method from Pueblo builders who'd used similar earthen ovens for centuries. The clay absorbed heat energy during active burning, then released it slowly through radiation rather than rapid convection. Unlike thin metal that heated and cooled quickly, thick earthen mass moderated temperature swings by storing energy during peak burning and distributing it over extended periods. Carter began experimenting that spring, building a crude prototype using clay excavated from his property, mixed with dried grass and water. He constructed a small test stove around wooden sticks in his workshop, firing it repeatedly to observe heat retention. The results encouraged him. The clay shell remained warm to the touch for hours after flames died, while a piece of sheet iron placed nearby cooled completely within minutes. His neighbors viewed these experiments with skepticism, bordering on contempt. Jenkins dismissed the clay stove as Mexican nonsense, arguing that American ingenuity had already perfected heating technology through industrial manufacturing. Why regress to primitive building methods when modern cast iron stoves offered proven performance and commercial reliability? The local supply agent, who profited from stove sales and replacement parts, actively discouraged Carter's experimentation. "That desert mud won't last one winter," he warned. "You'll be crawling back here begging for proper equipment when that contraption falls apart." Even the territorial newspaper, in a brief article about homesteading improvements, praised families who'd adopted modern heating apparatus rather than reverting to antiquated methods reminiscent of Aboriginal construction. Carter pressed forward despite social pressure, driven by practical necessity rather than stubborn pride. His fuel bills were unsustainable, and the iron stove's performance remained inadequate despite proper installation and maintenance. If traditional earthen techniques could solve problems that expensive manufactured equipment couldn't address, the ridicule seemed a reasonable price for genuine improvement. By autumn of 1879, Carter had constructed his first full-scale earthen stove inside the cabin, a clay and straw shell approximately 18 inches square and 6 inches thick, built around a stick framework that would burn away during initial firing. The design borrowed elements from Ramirez's Horno, but adapted them for interior heating rather than outdoor cooking. Carter had no blueprint or engineering manual, only empirical observation and traditional knowledge passed down through generations of builders who'd understood thermal mass principles long before cast iron foundries existed. The approaching winter would test whether frontier wisdom truly required factory-manufactured solutions, or whether older, simpler methods might prove superior when properly applied and understood. Winter 1879 arrived with Carter's experimental earthen stove installed, but untested under actual heating conditions. The construction had consumed 2 weeks of careful work, beginning with excavation of clay-rich soil from a deposit near the seasonal creek bed. Carter learned through trial that not all clay performed equally. The reddish adobe clay from the arroyo bottom proved superior to the gray surface clay, containing fewer impurities and binding more effectively with organic matter. The mixing process required precise ratios discovered through methodical testing. Carter found that 1 part, clay to 3 parts chopped grass, created a mixture too weak for structural integrity, while 1 part clay to 1 part, grass became too dense and cracked during drying. The optimal proportion, 2 parts clay to 1 part dried grass by volume, produced a composite material that maintained cohesion while allowing controlled shrinkage. He added water gradually, achieving a consistency similar to thick bread dough that held its shape when molded yet remained workable. Construction began with building the wooden framework from straight oak branches, each approximately 2 fingers thick and arranged in a rectangular pattern 18 inches square and 12 inches high. Carter lashed these sticks together with rawhide strips, creating a temporary skeleton that would burn away during the first firing, leaving hollow chambers within the clay shell. This technique, borrowed from Pueblo building methods, reduced the final weight while creating insulating air pockets throughout the mass. Carter applied the clay mixture in layers, building the walls outward from the wooden frame to a final thickness of 6 inches on all sides. Each layer dried for 24 hours before adding the next, preventing cracking from too rapid moisture loss. The process demanded patience. Rushing resulted in structural failures that required starting over. Carter learned to read the clay's drying signs. Surface lightening from dark brown to tan indicated readiness for the next application. The firebox opening required careful engineering. Carter shaped an arched doorway 8 inches wide and 6 inches high, small enough to retain heat but large enough for loading fuel efficiently. He reinforced this opening with a mixture containing additional sand, creating a more durable surface that wouldn't erode from repeated door opening and ash removal. A flat stone, heated and shaped to fit precisely, served as the door. Initial testing began in November with small fires to cure the clay gradually. Carter burned kindling for 30 minutes daily over 2 weeks, slowly increasing fire intensity to drive remaining moisture from the earthen shell without thermal shock cracking. Steam rose continuously from the clay surface during these first fires, confirming that moisture evacuation proceeded properly. Rushing this curing process would have destroyed weeks of construction work. The first full power test occurred during a cold snap in December 1879 when outdoor temperatures dropped to 18 degrees above zero. Carter loaded the firebox with seasoned oak, maintaining active burning for exactly 3 hours while monitoring interior cabin temperature with a mercury thermometer mounted on the wall 6 feet from the stove. At 10 o'clock, when he banked the coals and sealed the firebox door, the cabin measured 62 degrees. The earthen stove's thermal performance exceeded Carter's expectations. Unlike his previous cast iron stove, which radiated heat intensely during burning but cooled rapidly afterward, the clay shell absorbed energy slowly during the 3-hour burn period, then released it gradually over the following 12 hours. At 6 in the morning, 8 hours after active burning ceased, the cabin interior measured 57 degrees, a drop of only 5 degrees compared to the 25-degree drop he'd experienced with iron stoves under similar conditions. Fuel consumption dropped dramatically. Where Carter had burned nearly 3/4 of a cord per week during the previous winter, the earthen stove required only 1/3 cord weekly to maintain comfortable interior temperatures. The clay shell's heat storage capacity meant longer intervals between firings. Carter could load fuel once each evening rather than maintaining continuous burning throughout cold nights. The stove's surface temperature revealed the thermal mass principle in action. While cast iron reached temperatures too hot to touch within minutes of lighting, requiring constant vigilance around children and clothing, the clay shell warmed gradually to a comfortable level that provided steady radiant heat without burning hazards. Carter could place his palm against the exterior wall even hours after peak burning without discomfort. Carter documented these results methodically, recording daily fuel consumption, firing schedules, and temperature measurements in a leather-bound notebook. The data revealed consistent patterns. 3 hours of burning provided 12 to 14 hours of useful heat, with interior temperatures rarely dropping below 50 degrees even during the coldest nights. Total weekly fuel consumption averaged 1 1/4 cords compared to his neighbor's 2 3/4 cord consumption for equivalent heating. The clay shell's behavior during extended cold periods proved particularly impressive. When a 5-day cold snap brought sustained below-freezing temperatures, Carter's single evening firing maintained interior warmth throughout each night, while neighbors with iron stoves faced multiple daily firings to prevent interior freezing. The earthen mass stored enough thermal energy during peak burning to carry through extended cold periods without constant fuel feeding. Carter observed additional benefits beyond fuel savings. The clay shell eliminated the metallic ticking and popping sounds that iron stoves produce during heating and cooling cycles. Interior humidity levels remained more stable, as the earthen mass absorbed excess moisture during cooking and bathing, then released it gradually to maintain comfortable air quality. No condensation formed on cabin walls, a persistent problem during his iron stove winters. The construction proved surprisingly durable despite neighbors' predictions of rapid failure. The clay shell showed no cracking or structural deterioration after 2 months of regular use. Surface hardening occurred gradually as repeated heating cycles drove out residual moisture, creating an increasingly dense and stable exterior that resisted wear from ash removal and general handling. By February 1880, Carter's heating system had proven itself through sustained cold weather operation. The earthen stove consumed less than half the fuel of conventional iron stoves while maintaining superior interior temperatures and comfort levels. The investment of 2 weeks construction time had yielded immediate returns through reduced fuel costs and improved living conditions, validating traditional building methods against manufactured alternatives. The successful thermal mass application demonstrated that frontier heating problems required understanding physics principles rather than simply purchasing more expensive equipment. Carter had created a heat storage and distribution system using local materials and centuries-old techniques, achieving performance levels that contemporary industrial technology couldn't match under actual frontier conditions. Despite the clay stove's superior heat retention, Carter recognized significant inefficiencies during his second winter. Observation revealed that substantial heat escaped through the chimney flue, carrying away energy that should have transferred into the thermal mass. On windy nights, cold drafts infiltrated through gaps around the firebox door and flue connections, negating much of the thermal advantage he'd gained. The cabin's corners remained noticeably cooler than areas near the stove, indicating uneven heat distribution that conventional iron stoves also failed to address. Carter began studying the smoke path through his existing system, noting how hot gases rose directly from the firebox through a straight clay chimney tube he'd built into the shell's top. This direct route allowed combustion heat to escape rapidly rather than transferring energy into the surrounding clay mass. The principle resembled watching money flow through a poorly designed business, resources pass through without generating maximum benefit. His solution drew inspiration from German masonry heater designs described in a trade manual he'd acquired from a traveling peddler. European builders had developed labyrinthine flue systems that forced hot gases through extended pathways before exiting, maximizing heat transfer into surrounding masonry. Carter adapted this concept to his earthen shell construction, designing a serpentine smoke channel that would snake through the clay mass rather than escaping directly upward. Construction of the improved system began in autumn 1880 with careful planning of the internal flue pathway. Carter shaped the smoke channel using wooden forms, thin oak strips bent into curved sections, and positioned throughout the clay shell during construction. The pathway began at the firebox rear, curved downward along the shell's bottom edge, traveled horizontally across the base, then rose along the opposite side before connecting to the exterior chimney. Total internal pathway length measured 8 feet compared to the previous direct route of 18 inches. Building the serpentine flue required precise clay work to maintain proper cross-sectional area throughout the curved pathway. Carter learned that constrictions caused smoke backup, while excessive width reduced gas velocity and heat transfer efficiency. The optimal internal diameter measured 4 inches consistently along the entire route, large enough to prevent clogging from ash accumulation, but small enough to maintain adequate gas velocity for efficient heat exchange. The curved sections demanded specialized forming techniques. Carter soaked oak strips in hot water until pliable, then bent them into smooth curves without sharp angles that would create turbulence or ash accumulation points. He positioned these forms within the clay shell during construction, then carefully removed them after the clay hardened, but before complete drying. Timing proved critical. Premature removal caused tunnel collapse, while delayed extraction made removal impossible without destroying the shell. Carter addressed heat loss through the stove's base by constructing an insulating skirt around the lower shell. This technique, observed during visits to Jose Ramirez's adobe buildings, involved packing additional clay mixed with straw around the stove's foundation to prevent heat conduction into the cold cabin floor. The insulating layer extended 18 inches outward from the shell's base and measured 2 inches thick, creating a thermal barrier that kept stored heat within the living space rather than dissipating downward. The insulating mixture required different proportions than structural clay. Carter discovered that 3 parts chopped straw. To 1 part, clay created superior insulation while maintaining adequate structural integrity for the horizontal application. Too little straw reduced insulating effectiveness, while excessive organic matter created settling and gap formation. The mixture dried slowly due to reduced clay content, requiring 3 weeks of curing before achieving full effectiveness. Draft control mechanisms address the persistent problem of cold air infiltration during windy conditions. Carter fabricated a sliding damper plate from thin sandstone, sized to fit precisely within the serpentine flue's exit point near the exterior chimney connection. This damper allowed fine adjustment of draft strength, reducing excess airflow that carried away heat while maintaining sufficient ventilation to prevent smoke backup into the cabin interior. The firebox door received similar attention through installation of a fitted stone slab with clay mortar sealing around the edges. Carter shaped the door opening with beveled edges that created compression fit when the door seated properly, eliminating the gaps that had allowed cold drafts in his previous design. A simple wooden handle attached with iron wire provided safe operation without requiring manufactured hardware. Testing the improved system during December 1880 revealed dramatic performance gains over his previous earthen stove design. Interior temperature measurements showed the cabin maintaining 67 degrees 8 hours after fire extinction, compared to 58 degrees achieved by his earlier version under identical conditions. The serpentine flue successfully captured heat that previously escaped through direct chimney loss. Fuel consumption dropped to 3/4 of a cord weekly, a significant improvement over his previous 1 cord weekly requirement and drastically better than neighbors' continued 2 to 3 cord consumption. The extended flue pathway extracted maximum energy from each piece of burned wood, requiring less frequent firing to maintain comfortable interior temperatures during sustained cold periods. Surface temperature mapping revealed more uniform heat distribution throughout the cabin. The serpentine flue's pathway carried warm gases throughout the clay shell, creating multiple heat sources rather than concentration around the firebox area alone. Corners that previously remained uncomfortably cold now maintained temperatures within 5 degrees of the stove's immediate vicinity. Carter documented draft control benefits during variable weather conditions. The adjustable damper allowed optimization for different wind speeds and atmospheric pressure conditions that affected natural chimney draft. During high winds, partial damper closure prevented excessive airflow that would have rapidly consumed fuel while providing inadequate heating. In still conditions, full damper opening ensured complete combustion without smoke accumulation. The insulating skirt eliminated cold spots along the cabin floor where heat had previously conducted downward through direct shell contact with the wooden planking. Floor temperatures near the stove now remained comfortable for bare feet, while previously the immediate area had felt uncomfortably cold despite intense heat radiating from the shell's upper surfaces. Ash management improved significantly with the serpentine design. The curved pathway created natural ash collection points where Carter could periodically clean accumulated debris without dismantling any structural components. Monthly maintenance involved removing the damper plate and using a long wire brush to clear the horizontal flue sections, a simple process that maintained peak efficiency throughout the heating season. Carter's refined system demonstrated that incremental improvements to proven principles could yield substantial performance gains. The combination of extended heat exchange pathway, controlled draft, and thermal insulation transformed his basic earthen stove into a sophisticated heating system that extracted maximum benefit from available fuel while maintaining superior interior comfort compared to manufactured alternatives. By winter 1881, Carter's refined earthen stove had operated successfully for 2 heating seasons, but prolonged use revealed structural vulnerabilities that threatened long-term viability. Fine hairline cracks appeared along the clay shell's base where moisture from the cabin floor had wicked upward into the earthen mass. A February rainstorm, rare but devastating in the high desert, deposited nearly an inch of precipitation that saturated the ground beneath his cabin, causing visible dampness to seep through the clay shell's bottom sections. The moisture infiltration created multiple cascading problems. Wet clay lost thermal efficiency as water absorbed heat energy that should have warmed the cabin interior. The saturated earthen mass expanded and contracted differently than dry sections, creating stress fractures that allowed cold air to infiltrate and heat to escape. Most concerning, the damp clay became vulnerable to freeze-thaw cycles that could destroy the entire shell during a severe cold snap. Carter recognized that his current ground-level installation violated fundamental masonry principles he'd learned during his carpentry training in Pennsylvania. Stone foundations elevated buildings above grade specifically to prevent moisture migration. Yet he'd built his thermal mass directly against the wooden cabin floor where groundwater could easily reach the clay matrix through capillary action. The solution required elevating the entire stove system above potential moisture sources. Carter designed a raised stone foundation using flat sandstone slabs quarried from nearby outcroppings, creating a platform 8 inches high and extending 6 inches beyond the stove's footprint in all directions. This elevation placed the clay shell well above normal groundwater levels while providing thermal isolation between the earthen mass and the cold cabin floor. Construction of the stone foundation demanded precise leveling to prevent stress concentrations that could crack under the clay shell's substantial weight. Carter used wooden wedges and clay mortar to achieve perfect horizontal alignment across the platform's entire surface, checking with a carpenter's level borrowed from the territorial survey crew. Each stone required individual fitting and adjustment, a time-consuming process that consumed 3 weeks of careful work. The elevated foundation incorporated drainage channels carved into the stone platform's edges, allowing any moisture that did penetrate the system to exit rather than accumulating beneath the clay shell. These channels, barely half an inch deep but precisely angled, directed water flow toward the cabin's exterior walls, where it could evaporate harmlessly rather than pooling around the stove's base. Carter addressed the clay mixture's inherent vulnerability to moisture through reformulation that increased structural stability while maintaining thermal properties. His improved recipe incorporated river sand at a ratio of 2 parts sand to 1 part, clay to 1 part chopped straw, creating a more resistant composite material. The sand particles provided internal structural framework that prevented excessive expansion and contraction while maintaining adequate binding strength for thermal mass applications. The sand addition required careful sourcing to avoid contamination that could weaken the mixture. Carter discovered that fine river sand performed better than coarse desert sand, providing better particle distribution throughout the clay matrix. He screened the sand through hardware cloth to remove pebbles and organic debris that could create weak points or combustion hazards within the shell structure. External weatherproofing became essential for long-term durability in the harsh desert climate where temperature swings exceeded 40 degrees daily and occasional storms delivered intense precipitation. Carter applied a protective plaster coating 2 inches thick over the entire clay shell exterior using a mixture of clay, sand, and water mixed with lime obtained from a Mexican mason working on territorial government buildings in Los Angeles. The lime plaster provided superior weather resistance compared to plain clay, forming a harder surface that shed water rather than absorbing it into the underlying shell structure. Carter learned the lime application technique from Jose Ramirez, who demonstrated the traditional Mexican method of applying thin layers with wooden floats, building up thickness gradually to prevent cracking or delamination from the base shell. Air quality issues that had developed during the previous winter required systematic attention to combustion air supply and interior ventilation. Carter had noticed increasing problems with smoky interior air and incomplete combustion that reduced heating efficiency while creating uncomfortable living conditions. The problem stemmed from inadequate fresh air supply to support proper burning while maintaining cabin comfort. Carter's solution involved installing a dedicated external air intake system that provided combustion air directly to the firebox without drawing heated interior air up the chimney flue. He fabricated a 3-inch diameter clay tube that penetrated the cabin's exterior wall 18 inches above ground level, connecting to a chamber beneath the firebox floor where incoming cold air could warm before entering the combustion zone. The external air intake eliminated negative pressure problems that had plagued his earlier designs. Previously, the stove drew combustion air from interior sources, creating suction that pulled cold exterior air through floor cracks and door gaps. The dedicated intake maintained positive pressure within the cabin while ensuring adequate oxygen supply for efficient burning. Carter positioned the intake opening on the cabin's north wall to minimize wind-driven pressure variations that could affect combustion consistency. A simple hinged damper constructed from thin stone allowed adjustment of incoming air volume based on weather conditions and desired burning intensity. During extreme cold, partial damper closure reduced excessive cold air infiltration while maintaining adequate combustion support. Interior air circulation improvements accompanied the intake system modifications. Carter installed wooden baffles near the ceiling that directed warm air toward previously cold corners, creating convective loops that distributed heat more evenly throughout the cabin space. These simple angled boards, positioned to guide rising warm air along the walls and back toward floor level, eliminated temperature stratification that had left floor areas uncomfortably cold despite intense heat near the stove. The combined moisture control and air management systems underwent testing during the severe winter of 1882 when sustained below freezing temperatures challenged every heating system in the region. Carter's elevated stove remained completely dry despite ground saturation from snowmelt, while the controlled air intake maintained clean combustion and even interior heating throughout the extended cold period. Performance measurements confirmed the system improvement's effectiveness. Interior temperatures measured 69 degrees at dawn following 10-hour periods without active burning, representing steady advancement over his previous designs. Fuel consumption decreased to 3/4 cord weekly despite the challenging conditions, proving that systematic engineering refinements could achieve continuing efficiency gains. The structural modifications demonstrated exceptional durability throughout the harsh winter conditions. No visible cracks appeared in the lime-plastered shell surface, and moisture infiltration remained completely eliminated despite several storm cycles that tested the elevated foundation and drainage systems. Carter had successfully transformed his experimental clay stove into a permanent, reliable heating system, capable of outperforming manufactured alternatives under sustained frontier conditions. The winter of 1883 arrived with unusual severity across the southwestern territories, bringing weather patterns that challenged every heating system from the Colorado River to the Pacific coast. A massive Arctic air mass descended from Canada in late January, establishing a high-pressure system that trapped sub-zero temperatures across the high desert for unprecedented duration. Weather stations in Los Angeles recorded the coldest temperatures in territorial history, while remote homesteading areas experienced conditions that tested the limits of frontier survival. Carter faced this extreme weather with confidence in his refined earthen heating system, but the crisis extended beyond simple temperature challenges. A late-season blizzard had blocked mountain passes, preventing the scheduled firewood deliveries that supplied most homesteaders through winter's end. The Mexican woodcutters, who typically hauled oak and pine from higher elevations, found their wagons stranded by snowdrifts that measured 6 feet deep across critical road sections. Samuel Jenkins, still relying on his Detroit cast iron stove, had calculated his fuel needs based on normal winter consumption of 3 cords total. By mid-January, he'd already burned 2 3/4 cords, leaving insufficient reserves for the extended cold period. The supply disruption meant no additional wood would reach the settlement until spring thaw opened the mountain routes, potentially months away. The Kowalski family faced similar desperation with their Pittsburgh iron stove having consumed nearly their entire winter wood supply. They began burning furniture legs and floorboards to maintain minimal interior heating, knowing that complete fuel exhaustion meant abandoning their claim or risking death from exposure. Other homesteaders throughout the region confronted identical calculations as supply shortages coincided with unprecedented heating demands. Carter's fuel situation provided stark contrast to his neighbor's crisis. His earthen stove's efficiency improvements had reduced consumption to half a cord weekly, even during normal cold periods. When the extreme weather arrived, his thermal mass system required only slight increases in burning frequency to maintain comfortable interior temperatures. His fuel reserves, calculated for normal winter consumption, proved adequate for the extended emergency conditions. The temperature monitoring that Carter had maintained throughout previous winters now provided crucial data for comparing system performance under extreme stress. On January 28th, when outdoor temperatures dropped to 14 degrees below zero with 30-mile-per-hour winds, his cabin interior measured 68 degrees at 10 o'clock when he banked the evening fire. 8 hours later, the interior temperature had dropped to 59 degrees, a decline of only 9 degrees despite the brutal exterior conditions. Jenkins's cabin, measured with Carter's thermometer during a welfare check, recorded 28 degrees at 6 in the morning after identical outdoor conditions. His cast iron stove, burning continuously throughout the night and consuming his precious remaining fuel, could not maintain interior temperatures above freezing. Ice formed on interior walls within 10 feet of the active stove, while water buckets froze solid despite positioning directly beside the firebox. The Kowalski family's situation proved even more desperate. Their fuel rationing strategy, designed to extend supplies through the crisis, resulted in interior temperatures dropping to 18 degrees during the coldest nights. They survived by remaining in bed under multiple layers of clothing and blankets, emerging only to feed minimal fuel into their stove. 3 of their chickens froze to death in the attached lean-to despite crude heating attempts. Community response to the crisis revealed the social dynamics that had shaped attitudes toward Carter's experimental methods. As fuel shortages became critical and neighbors faced genuine survival threats, previous mockery transformed into urgent interest in his earthen stove's performance. Jenkins, who had dismissed Carter's system as primitive Mexican nonsense, now asked detailed questions about clay mixture ratios and construction techniques. The territorial supply agent, who had predicted Carter's desert mud would fail within one winter, quietly inquired about obtaining construction plans for earthen stoves. His commercial stove inventory remained unsold, while desperate homesteaders sought alternatives that used available local materials rather than requiring expensive manufactured equipment that supply disruptions made unavailable. Carter documented the performance comparison systematically, recording daily measurements that quantified his system's advantages. Over the 48-hour peak cold period, his earthen stove consumed 3/4 of a cord while maintaining interior temperatures above 55 degrees continuously. Jenkins burned 1 1/4 cords during the same period while achieving interior temperatures that averaged 32 degrees, exactly at the freezing point where water and food supplies became unusable. The repair and maintenance requirements during extreme conditions provided additional evidence of the earthen system's superiority. Carter's stove required no parts replacement or structural repairs throughout the crisis period. The lime-plastered shell showed no cracking or deterioration, despite thermal stress from increased firing frequency. The elevated stone foundation prevented any moisture-related problems even when snow accumulation around the cabin created potential infiltration sources. Jenkins's iron stove suffered multiple failures during the extended use period. The firebox door warped from overheating, creating gaps that allowed heat loss and cold air infiltration. A section of stovepipe separated from thermal expansion, requiring emergency repair with clay mortar to prevent smoke infiltration into the cabin interior. The ash pan cracked from repeated rapid heating and cooling cycles, making ash removal difficult and messy. Knowledge transfer began immediately as the crisis demonstrated earthen heating superiority beyond dispute. José Ramirez, whose traditional building knowledge had contributed to Carter's system development, found himself instructing multiple homesteader families in clay, mixture preparation, and shell construction techniques. The Mexican mason's expertise, previously dismissed by Anglo settlers as backward, now commanded respect as families sought survival alternatives. Carter shared his construction methods freely with neighbors facing fuel shortages and heating system failures. He provided detailed guidance on foundation preparation, clay shell building, and flue design, recognizing that community survival benefited everyone's long-term prospects. His notebooks, filled with temperature measurements and fuel consumption data, served as technical manuals for families attempting to replicate his success. The regional impact extended beyond individual homestead applications. The territorial newspaper published a detailed article describing Carter's earthen stove system, including construction specifications and performance data from the winter crisis. This documentation reached homesteaders throughout the Southwest, spreading traditional building techniques to communities facing similar heating challenges and fuel supply limitations. By spring 1884, 7 families within the immediate settlement had constructed earthen stoves based on Carter's refinements. These installations incorporated the complete system, elevated stone foundations, serpentine flue pathways, lime plaster weatherproofing, and controlled air intake mechanisms. The local adoption rate demonstrated how practical necessity overcame cultural prejudice against traditional building methods. The long-term legacy extended into the 20th century as earth and heating systems became established alternatives throughout the arid Southwest. Homesteading manuals published in the 1890s included detailed instructions for clay stove construction, crediting Carter's systematic documentation and successful community demonstration. Archaeological surveys of historic homestead sites continue to identify earthen heating systems that follow the technical principles Carter developed through his methodical experimentation and refinement process.